Now the next probability distribution function that we'll look into is the chi-square distribution. So let's consider x to be a vector consisting of n independent random variables xi each distributed normally. So which also means that they follow the Gaussian distribution, and each of them have mean mu I and variance sigma I square. So in this case, the joint PDF, the joint PDF is written as the random variables are denoted by the vector x, and the parameters would be again captured by these vectors mu and sigma. So this is simply given as a product of n terms, each of which follows a Gaussian distribution. And of course, this product over exponentials can also be rewritten as the exponential of a sum and this product sits on the outside. Now we can define a variable chi-square as follows. So notice that this chi-square I've written as a function of n, where n characterizes the upper limit of the sum. Since chi-square is a function of random variables, chi-square itself is a random variable. Now this parameter n in this context is known as the degrees of freedom, because for each of the random variables xi is free to vary independently of the others. Now, one thing to note is that chi-square is referred to as the variable, not the square of a variable. So we did not bring any chi, which is the square root of this chi-square, into the discussion. So now let's look at it case by case for different degrees of freedom. So let's start with chi-square with 1 degree of freedom. So, which means n equals 1. We define z as x minus mu by sigma. So the PDF for z is nothing but the normal distribution for the random variable z with mean 0 and standard variance 1. And the probability that capital Z lies between interval of Z and Z plus dz is given by fz dz, where we identify fz as 1 by the square root of 2 pi times e to the power minus half z square. Now let's define q as z square. And notice this is not a one-to-one transformation. And this is because both plus and minus z map to q under this transformation. Now the probability that q lies between small q and small q plus dq is actually the sum of the probabilities that z lies between z and z plus dz at z equals to root q, as well as at z equals minus of root q. So we must add the PDFs obtained from plus z going to q transformation as well as minus z going to q transformation. Now if you look at the Jacobians for these two transformations, let's denote them by j plus minus. This is d for plus minus z with respect to dq. This can ultimately be written as 1 by 2 root q. And then f of q dq is 1 by root 2 pi exponential of minus q by 2. We take into account both the transformations. And that basically allows us to write all in all, it comes out to be 1 by the square root of 2 pi q c to the power minus half q dq. Q was nothing but the chi-square variable. So the PDF for chi-square with 1 degree of freedom, so chi-square 1, so f in terms of chi-square 1 is 1 by 2 pi chi-square e to the power minus half chi-square. Now notice that we are using the same symbol chi-square for the random variable as well as its PDF. Next, if we have n equals to 3, that is chi-square with 3 degrees of freedom, So we'll work with standardized normal variables. Zi equals xi minus mu I by sigma I. And we define r square equals the chi-square variable, which is z1 square plus z2 square plus z3 square. And the joint probability in this case is given as so we'll get 3 factors of the square root of 2 pi. So 1 by 2 pi to the power 3 by 2. We basically added the arguments of the 3 exponentials. So product of exponentials equals exponential of the sum of the same arguments. Now we can think of capital R, especially based on this definition, as the radius of a sphere in 3-dimensional space. In such a case, we can rewrite the integration measure dz1 times dz2 times dz3 in spherical coordinates. It's dr square dr d cos theta d phi. Now to get the marginal PDF, for only r, you must integrate over cos theta and phi, which basically yields a factor of 4 pi. Therefore, the probability that r is between r and r plus dr is given by this distribution times the measure of the integration now chi-square is identified as r square in the current example. So therefore, d of chi-square is basically 2r times dr, or we can rewrite dr as d chi-square times twice of root chi-square. So we can rewrite the distribution in terms of chi-square as f of chi-square is 3 to denote the number of degrees of freedom. Chi-square, this is 2 by 2 pi the root chi-square e to the power minus chi-square by 2 d chi-square. We have twice of square root of chi-square. Or in other words, this chi-square distribution for 3D UFs is simply given as chi-square to the power 1 by 2 root 2 pi e to the power minus chi-square by 2. Ultimately, if we want to generalize this to n degrees of freedom, so let's say we want so then this basically becomes chi square to the power n by 2 minus 1 exponential of minus chi square by 2, and as the denominator we have a gamma function, and to the power n by 2. So if we want to discuss some of its properties, and those are given as the mean simply comes out to be n, the variance comes out as twice n, and the skewness is given by 2 root 2 by root n. The kurtosis is given by 12 by n, and the characteristic function is described as 1 minus 2it to the power minus n by 2. Let's see whether this has reproductive property or not. So if chi I square is a set of variables distributed as chi square ni, so there are different degrees of freedom in each case, then the sum over the chi I squares is distributed as the chi square of sum over ni. So a chi square distribution with these many degrees of freedom. And the variables chi 1 square and chi 2 square by definition are given like this. So therefore, if you look at their sum, that's nothing but the sum over zi square. I goes from 1 to n1 plus n2. Which from definition is nothing but a chi square with n1 plus n2 degrees of freedom. The expectation of chi square n is n, and this implies that the expectation of chi square n by n is 1. Now this quantity chi square n by n is known as reduced chi square. If we talk about the asymptotic limits, and for large n, the chi square PDF approaches the normal distribution with mean n and variance 2n. Even faster convergence occurs for the variable square root of 2 chi square, for which we basically get normal distribution with random variable root 2 chi square, mean 2n minus 1, and variance 1. And this approximation works for n greater than 30 or something. But in all these definitions, the Gaussian variables were independent. So how do we give a general definition for chi-square? So if the n Gaussian variables are not independent, we can always change variables so that the covariance matrix is diagonalized. Now this is a unitary transformation. So that implies the covariance ellipse is given by G equals to K. G we defined earlier. So this does not change. And in the diagonal case, G is simply chi-square. So therefore, in the correlated case also, chi-square should correspond to G. So we can take chi-square equals x minus mu transpose V inverse x minus mu as the general definition for the random variable chi-square. Now, let's move on to another distribution. It's popularly known as the student's T distribution. So consider a random variable x that is normally distributed with mean mu and standard deviation sigma. So Of course, we know that this implies that a variable z, which is defined as x minus mu by sigma, follows the normal distribution with mean 0 and standard deviation 1. So in the normal probability distribution function, the mean determines the origin, and the standard deviation determines the scale. So when we transform from x to z, both these dependencies are removed. When we analyze data, we may not know the standard deviation. So we may then remove the scale dependence by using the sample standard deviation instead of the parent standard deviation. Similarly, we may not know the parent mean and we'll use the sample mean instead. So for n independent xi's, we have this sample standard deviation or the square of it, which is actually given as so this is if we use the mean, or we have the definition by n minus 1, sum goes from I equals 1 to n, xi minus x bar square. We basically used x bar as the arithmetic mean of the random variables. Now in either case, n times this standard sample standard deviation divided by the standard deviation is distributed according to chi-square. For capital N minus k degrees of freedom, where k equals 0 if we use the mean, and k equals 1 if we use the arithmetic average, because in the latter case only n minus 1 of the terms in the sum are independent. So now we want to see what is the probability distribution function for the random variable. So if we define t x minus mu by sigma hat, or in other words x minus mu by sigma by n sigma hat square by sigma square, we basically divided by sigma in both the numerator and denominator, and the denominator we have multiplied and divided by root n. So this can be rewritten in terms of the standard variable z. We identify the chi-square, chi-square by n. Now z is a standard normal random variable. chi-square is just chi-square with n degrees of freedom. So a student's t random variable is the ratio of a standard normal random variable to the square root of a reduced chi-square random variable. Now if you look at the joint PDF, for z and chi-square, to get is something like this. We express the PDF of z as the Gaussian, and we use the general formula for the chi-square with n degrees of freedom. So we have assumed that z and chi-square are independent, and this is so if x has not been used in determining sigma hat, and asymptotically true if n is large. Now we make a change of variable based on this relation, and we rewrite this distribution as 1 in terms of t and chi-square. So or directly using t equals z by chi-square by a. So this allows us to write f of t and chi-square with n as a parameter. From this joint PDF, we can get the marginal PDF for t by integrating over all chi-square, and that is what leads us to the student's t distribution. If you look at its properties, the mean is 0 for n greater than 1. The variance is n by n minus 2 for n greater than 2. The skewness is 0, meaning it is symmetric about the mean. The kurtosis is given as 6 by n minus 4, the requirement that n should be greater than 4. And lastly, if we look at a general formula for the moments, let's call them mu r. And under different conditions, it takes different values. So these ratios of gamma functions, this occurs if r is even and r is less than n. The moments are 0 if r is odd and less than equal to n. In all the other cases, the moment does not exist. So the student's t distribution is the probability distribution function of a random variable t, which is the ratio of a standard normal variable and the square root of a normalized chi-square random variable for n degrees of freedom. So the number of degrees of freedom n is not required to be an integer. The t distribution with non-integral n greater than 0 is useful in some applications, but we won't go into the details. The student's t distribution is symmetric about t equals to 0, and it approaches the standard normal distribution as the number of degrees of freedom approaches infinity. Now, just like we have constructed t from a single observation x, we can do the same for a number of random variables, each distributed normally with mean mu and standard deviation sigma. It's because of the reproductive property of the normal PDF that vector x will also be normally distributed with mean mu, but with a standard deviation of sigma by root n. So you can do a generalization here. The last distribution that we want to discuss in this context is the F distribution. So for this we consider two random variables. We denote them as chi1 square, chi2 square, each of them distributed as chi square. With, let's say, nu1 and nu2 degrees of freedom. Now we define a new random variable as a ratio of the two reduced chi-squares. So it will be chi1 square by nu1 by chi2 square by nu2. The derivation for the F distribution is also similar to what was used for the student's T distribution. We'll start with the joint PDF of the independent variables, make a change of variable to F, we define one auxiliary variable in terms of chi2 square and then integrate out the dependence on the auxiliary variable. The result basically comes out to be This distribution is known by many names. So it's known as the Fisher-Snedecor distribution, or only as Fisher distribution, or only as Snedecor distribution. It's also known as the variance ratio distribution, or simply as the F distribution. Now, if you look at the properties, the mean is given as nu2 by nu2 minus nu1. Probability is nu2 should be greater than 2. The variance denoted by V of f, it's 2 nu2 square nu1 plus nu2 minus 2 divided by nu1 times nu2 minus 2 whole square, nu2 minus 4. The requirement nu2 should be greater than 4. And the distribution is positively skew and tends to normality as nu1, nu2 both tend to infinity. But this happens only slowly. Instead, if you look at the PDF for a logarithmic form, so it's a PDF of z, if you define z as half log of f, and this approaches a Gaussian with mean of and variance So this is where we'll end our discussion of probability distribution functions. In the next lecture, we'll try to see what we encounter in real-world applications and how real-world situations differ from or are similar to what extent they are modeled by these various probability distribution functions that we have studied so far.